Okay, there are two basic systems by which electricity is generated in the world today. One is a basic power plant like we've been doing since the 1930s. The other is known as a combined cycle system. We're not going to talk about that today. All right, that's a different subject altogether. In the basic power plant that you see today, you have a heat source. It could be anything, okay? It could be fueled by coal. It could be fueled by natural gas. It could be fueled by fuel oil. It could be nuclear. You could have a heat source here that was nuclear power. Doesn't make any difference. We're not going to talk about nuclear power, but the fact is that you've got a fuel source here, and you take a hydrocarbon fuel and you burn it with air in a burner, and that converts the fuel into energy. Okay? The gases here, when you take a fuel and you burn it, you take the fuel and you turn it into two things. You get CO2 and you get water. So whenever you burn a hydrocarbon, you're taking the hydrocarbon in the fuel, you're combining it with air, and you're getting water, you're getting CO2, and you're getting heat. All right? So that heat here is around 2,500 degrees Fahrenheit, right here. Okay? And the gases coming off here are water and CO2. Those are called combustion products. They move through the boiler. They start off down here at around 2,500 degrees Fahrenheit. When they're exiting the boiler, they're exiting at around probably 1,300 degrees Fahrenheit. This boiler here converts liquid water into steam. That steam comes off of here, and that steam is around 1,100 degrees Fahrenheit, and it's around 1,000 psi. It's called a high-pressure turbine. So you have steam here that is around 1,100 degrees Fahrenheit, and it's at about 1,000 psi, and it's pushing the turbine. The turbine turns. The generator generates electricity. Now the gases that are exiting here in the 12 to 1,300 degrees Fahrenheit range still have an awful lot of energy in them. So what they have done and they started doing this in the 60s, was they started adding a low pressure system on top of the high pressure system that would take those gases and convert and extract more energy out of them. All right. This was a big deal in the 60s on making, and it's part of how they controlled acid rain all those years ago, if you ever heard of that. They added low-pressure boiler systems. They made them a lot more efficient, and it also made it easier for them to capture and scrub the byproducts. But the thing that happens in a low-pressure boiler is that these gases coming through here, okay, start at around 1,200 degrees Fahrenheit. They exit at around 800 degrees Fahrenheit. They take the water in these boiler tubes, and they make steam that's around 600 degrees Fahrenheit and around 600 psi. So here you have steam that's around 1,100 degrees Fahrenheit and around 1,000 psi, and here you have steam that's around 600 degrees Fahrenheit and around 600 psi. And here you have, going up the stack, okay, you have, as it comes out of the stack, right, what you have is combustion products that were 2,500 degrees down here and they're 800 degrees here. Now what that means is in this system here, you're losing almost a third of the energy right up the stack. Now, these days, this doesn't go straight up the stack. It goes to scrubbers that pull acid out of it. It goes to various different things that clean it up from an environmental standpoint. But the point that I want to make here is that 1/3 of the energy is lost when the combustion products leave the low pressure turbine. Now, the high pressure steam and the low pressure steam both act on the turbine blades and generate electricity, and then they get exhausted. Okay, the turbine exhaust from the low pressure side is combined with a turbine exhaust from the high pressure side, and it goes to a condenser. Now, these are operating at a whole different situation. They're operating at a slight vacuum. They're running about 5 psi below atmospheric. All right, is where these operate, and that means that the temperature coming off here is around 200 degrees Fahrenheit, and the temperature coming off here is around 200 degrees Fahrenheit. Okay, and the pressure is around 5 psi, which is below atmospheric. That goes to the condenser, which takes the vapor and condenses it back to liquid. Now, water as liquid has a lot less energy in it than water as vapor. All right. At the pressures and temperatures we're talking about, there are in fact about 800 BTUs a pound in steam, and there's about 60 psi per pound in the water. So when you take that liquid the steam and turn it back into a liquid, you lose that energy. It's why we have red arrows here. That red arrow represents the energy lost from the boiler. And these red arrows represent the energy lost in the condenser. The liquid water coming off the condenser, okay, goes to a boiler feed pump and is pumped back into the boiler. All right, so that's the cycle. It starts here. You have steam to a turbine, to a condenser, to a boiler feed pump, back to the boiler. That's called the Rankine cycle for whatever reason. A guy named Rankine invented the cycle probably in the late 1920s and got named it after him. But that's the deal. You're losing energy here and you're losing energy here. In a standard power plant, only between 30 and 40% of the energy actually contained in the fuel turns into the equivalent energy in electricity. The other 60% goes back into the environment. And that's the important thing for you to know as we move into discussing the 4 technical advances that we have made that make Sundancer possible.